The guy who shares his office with me, Benno Verschuren, is a very talented designer, and for a few style frames he needed to set up which turned a hexagonal grid into Voronoi cells. And I think this is a really neat setup for a beginner, for a person who wants to get into Houdini, because it requires very little to no scripting, while at the same time it shows the basics of how you tackle such a setup in a procedural 3D app such as Houdini. To get started, I will drop down a grid and dive in there. Let's disable this viewport grid and increase our rows and columns to say 40 by 40. I want to duplicate this grid, copy it over here, and want to set this to only have 2 rows and 2 columns, so one big polygon. And what I can do now is drop down a Voronoi fracture node and wire up both grids in here, with this grid providing the Voronoi fracture points for this grid. So those are really regular, and the Voronoi fracture will spit out a very regular grid as well. So basically the position of these points here will drive how my Voronoi fracture looks. So let's highlight this grid again and modify it to spit out a hexagonal subdivision in the Voronoi fracture. And for that I want to move every second line of that grid to the side. Let's do that by first dropping down a group by range, so I can select every second line basically. And what I want to do is, I want to select 40 points out of 80. And not primitives, but points, like this. And let's call this one move, so the group of points that I want to move now. Let's use a transform, wire this in here underneath the group, and in the group tab just select the move group that we created here, and then increase the translate along X, and of course I have to highlight this first so I can see I'm now translating every second point here. So when I highlight the Voronoi fracture now and keep dialing in the points here, you can see I can set up something along the lines of a hexagonal. That needs a bit dialing in there, like this. So let's set this to 0.125, and I get this hexagons here. So in order to get this typical Voronoi look, I'll have to randomly move those points that I feed in here. So I can do that with the point jitter node, which I'll wire in here, highlight it, and you can see this messes it up really badly, so let's dial back the scale. And also when looking at it from the side, I want to scale the y-axis to 0, so it's only moving in the x and z direction. Again, decrease the scale a bit further, like this. Highlight the Voronoi fracture again, and when I move the scale slider now, you can see we're pretty soon getting these typical Voronoi cells here, which basically just originate from randomly distributed Voronoi center points that I feed into the Voronoi fracture. So let's control this to give this a point around which my Voronoi fracture points will start to get jittered. And when I look at the point jitter, I have this checkbox here. It's called use p-scale. And what that says is, if I have a point attribute written on those points that come into the point jitter here that's called p-scale, it will use that to drive the overall scale of the point jitter effect. Let's try that by creating a point attribute with the help of the attribute create. Wire this in between here, and let's set our attribute to have the name p-scale, be a point attribute. By default it should be 0, but for now let's set it to 1. Go into the point jitter and check use p-scale, and nothing should change because we just set our p-scale attribute to 1. However, if we dial back the p-scale value now, you can see the overall effect gets controlled by this p-scale attribute. So let's put that to use, and let's set its value to 0 for now. And what I want to do in here is I want to wire in an attrib transfer, which will accept a second stream of points and will try to match their attributes to our current geometry, which is this here. So let's add a single point. For now at the origin, copy over this attrib create here, wire this into our point, and set the point's p-scale value to 1, and then wire it in the attrib transfer here. So let's highlight that, no error again. Same goes for the point jitter here. However, that only partially worked because all my points are kind of uniformly jittered. So let's have a look at the attrib transfer again, drag this down and go into the conditions tab here. So under the distance threshold, if we dial that back, we can see the radius around which our points attribute get transferred gets smaller. So let's set this to 1.5 like this, and again highlight our Voronoi fracture, and we can see now we have this area in which we have this typical Voronoi cell look versus this area where we have the regular hexagonal grid. And if I move around my add point here, I can move around that whole effect. I can scale it, of course, with the distance threshold, but what I want to do now is have it kind of fall off here. This is kind of harsh, and to visualize this, let's drop down a visualize node. Wire attrib transfer in here, highlight this, and under the visualizers tab, let's highlight the p-scale. So we can see this is really harsh here. And there are several ways of dealing with that. I like to use the new attrib blur, which will just blur out those attributes that we feed it in our case, p-scale. Let's wire the visualizer underneath the attribute blur, and we can see already this has been blurred out quite a bit. And if we increase the blurring iterations, it'll get blurred out further like this. So now if we hit the point jitter, we can see this fall off to the sides. And in the Voronoi fracture, we can see the Voronoi look just fading, blending with those hexagonal grid cells. Again, let's increase the blurring iterations to maybe 32, and we now have this really smooth transition from our hexagonal grid to our Voronoi cell look. So that is building your basic transition from a regular grid to a Voronoi cell look using only Houdini standard subs. So no scripting involved here. Would I typically build it like that? Well, likely not. Instead of doing these 4 nodes here, I would just simply drop down a single point triangle and write this in VEX. So let's just quickly save this. And let's have a look at how I do it using a point triangle. So drop down a point triangle, and let's maybe copy this whole tree here, paste it, so we can see what's different. Alright, let's get rid of all of this here. Instead, wire in the point triangle in here, and wire the add sub in the second slot, and the visualize goes beneath it, like this. And in the point triangle, what I want to do, for each point on this geometry, I want to find out the distance to this point here. So let's get this point's position here. And we know this is the point coming in through the second slot with the ID 1. And this is the single point on this stream, so it's got a point number of 0. With that, let's create a vector, call it npos, and just load up the attribute out of the second input. Attribute is called p, and the point number is 0, like that. Let's create a float, call it d for distance. Let's calculate the distance of my grid point, so be at p, to our single point here. Let's create 2 floats and also create sliders for those. Call one max for maximum distance. Create a float slider, call this one max underscore distance. Just copy this, paste it, call this one minimum distance, and call the float min. Create those sliders. So I have a min and max distance. Set the max distance to 2. Next, I'll remap my distance to be in the range of 0 to 1 using those max and min sliders. So I'm going to write d equals 2. And let's use the fit function. And we want to fit d, which ranges between min and max. And we want it to be between 0 and 1. Finally, let's add a ramp to it to control the fall off of this one. chramp will give us a ramp interface, call this one fall off, and we want to remap d itself. Let's create the interface like this, which by default is set to be a linear ramp. Okay, finally, let's write d onto our p-scale attribute, so f at p-scale equals 2d, and it's p-scale, not p-scale, like this. And now I can see my visualize attribute here, and I've written this the wrong way around. Of course, where the distance is 0, I want the p-scale to be 1, and where the distance is 1, I want the p-scale to be 0. So let's just switch our remap range here. Instead of ranging from 0 to 1, let's range from 1 to 0, like this. And now I have these simple sliders where I can dial in maximum and minimum range, and also this neat curve interface where I can dial in the fall-off behavior. And from there on, it's just the standard setup, jittering the points, and then feeding this into a Voronoi fracture. So these are the 2 setups. And yes, I sincerely mean that this, for me, the point triangle, is easier than these 4 nodes here. And it's not because I want to minimize my node count, by no means. It is just, with this point triangle, all I have to memorize is VEX. And VEX is pretty close to standard C or C++. It's a C-style language. And VEX permeates every aspect of Houdini. So if you know VEX, you can not only drive points, you can also drive primitives, you can drive shaders, volumes. You can also drive the compositing with it, and also use it to create animation curves and chops. Also, VEX is logically structured, because it's very close to C, it's a C-style language, and it's very well documented, if you know how to read a programming language documentation, a reference. So, whatever style you choose, this is the simple, straightforward setup to turn a regular grid into this Voronoi cell look. As always, I'm excited to see what you guys use this for, what you guys come up with. If you want to learn more about VEX or the intricacies of Houdini, or in general if you want to support us, head over to our Patreon where we have some in-depth courses on topics like VEX, volumes, vellum, or in general, transitioning to Houdini, adding Houdini to your arsenal. And if you're already on Patreon, thanks so much for your support, and a very special thank you goes to Kyoko Sakane, Important Looking Pirates, Joseph Howerton, Derek A. Johnson, Nick, Chris Hebert, Refik Anadol, Rob Bryant Jr., and Mohammed Alabri. Thanks so much, guys. And with that, it's cheers and goodbye.